it's really a pleasure to be here virtually and talk to you a little bit about some of our work on privacy and synthetic data. So I'll start with, sort of a high-level overview of the ecosystem. So, as someone who has worked in privacy technologies for, more than 15 years, always, the need and the call for data sharing techniques is very recurring, right? So we all would like to have some kind of mechanism that allows us to take some data set, let's call it, raw data set, and allow analysts to extract, some statistical insights from this data set. So give access to, analysts from this data in a way that we can keep bad guys, malevolent actors out of the picture. And so one way to do it, so to share this data safely, we'll have to have some sort of magic silver bullet, some really cool, amazing algorithm that allows us to do so that in a way that we can share the data, but not put the privacy of the individuals, organizations, entities, and so on, whose data is being shared at risk, right? So, and this is really something that the community has attempted to, or at least strive for, really for many, many years. So really, this is, I think the first attempts were, really focused on anonymizing the data set. And so really, we thought that there were, we could build effective ways to anonymize or de-identify data sets by sort of removing the obvious and maybe not so obvious characteristics of the data that would be sensitive or that would make it easy to identify any individual. Unfortunately, this turns out to be not really a viable, very successful story, and there is a lot of sort of incidents that that have high-profile incidents that have unfolded over the years. So sort of removing, say, identifiers from data sets does not really mean that that you're protecting privacy correctly. If anything, because there is a lot of attributes in those data sets that can be reconstructed using other highly correlated data set, highly correlated features, and more. So these are just like a few examples of sort of the high-profile cases that affected large companies like AOL and Netflix, or even sort of government entities like the U.S. Census Bureau. So overall, anonymization, is not really the focus of my talk. So I just, you kind of have to believe me that it's not really something that works very well across, sort of across the board. Okay, and this has motivated the introduction of techniques to generate synthetic data. So there is a number of companies, actually, some in the US, some in the UK and elsewhere, that have really attempted to bring this into the market. So the idea is to, really, instead of sharing, sort of anonymized, sanitized versions of a data set, you share a synthetic version of that data set, so that you sort of remove any correlation with the raw data sets, but you still preserve statistical properties of the data set that may be interesting to the analyst. And this has really, I think, taken off since even like the NIST, the US National Institute for Standards in Technology has organized a challenge for differentially private synthetic data generation, and there's been a lot of sort of breakthrough in this field. So, and actually there is initiatives in the UK too. Sorry, I just had one slide here, one box here. So, for instance, the NHS, the UK National Health System has worked with a number of organizations to produce synthetic data sets for A&E, so emergency department data for like admission and discharge. So if I, to summarize, visually what I just discussed, really the idea of synthetic data is to take the raw data set and learn an approximation of the distribution of the data set. And this is done through generative machine learning models. And you sample from that model so that you can produce a synthetic version of that data set. Again, the idea is that the data set has artificial, fake data, but some statistical properties that you're interested in are still preserved in the synthetic data set. So, classic example is you're maybe not really interested. Let's think about mobility data, since this is Nokia. You're not necessarily interested in knowing which user is in which location at any time, but you might want to know how many users are, let's say on in tube stations, train stations, within a 15 minutes interval, right? So in this case, you don't really care to operate with real, user traces and user identities, but it's okay to preserve, the statistical distribution of, aggregates. Okay. So unfortunately, despite like I said, there's been a lot of breakthroughs and a lot of, great research in this space. We also have seen a number of attacks against generative models, against synthetic data. And in particular, I will tell you about one attack, just because that's the one that we were the first to present. And it's called a membership inference attack. Well, I'm joking. So membership inference attack is actually a very easy to explain attack, and is sort of used as a measuring stick to understand whether or not machine learning models leak information. Okay. So I take a step back here and I tell you a little bit about sort of membership inference attacks and information leakage in sort of generic machine learning models and sort of the more traditional discriminative models where you're typically training a model to perform some classification, right, rather than regenerating samples. So, and this is like a very large body. There is a very large body of work that comes from really this advent of machine learning as a service, where you have large cloud providers like Microsoft, Amazon, Google, and so on, that train machine learning models using their own data or data acquired by third-party users, and then provide API access to these models to maybe paying users, right? So that allows users who don't have the resources, the expertise, or the data to train their own model, let's say to do housing price prediction, to just ask Amazon to help them with that. So these are sort of discriminative models examples. So you provide an input like some information about a house, and the model returns some predictions. Or you do image classification and say you provide an input picture of an animal, and the model tells you which animal is that. Is that a cat? Is that a dog? And things like that. So a few years ago, Stochastic showed that these predictions can be leaky, so that by looking at the confidence scores provided by the prediction APIs, you can detect which records were used to train that model, and that's that is done. I'm oversimplifying a little bit, but that's done by means of detecting overfitting to the training data. So what does that mean? So again, let's take an example of image recognition model. The way it works, you provide an input like the image of a penguin, and let's assume there is like 4 possible labels that can be given to this image. The model will give you the confidence scores for each of the 4 possible labels. So you can see penguin, is likely to be, this image is likely to be a penguin with 75% probability, right? And the other labels are not so probable, right? So the idea is that, for images that were used to train the cloud model, the model is likely to overfit. So here you see a picture of a blue house and a picture of a red house. Here you can detect that the red house was actually used to train the model because the confidence score is really, really high. It's like almost 100%, right? Whereas for the blue house, it's maybe just over 60%. Obviously, I'm oversimplifying here, but I hope you get the point. So now, how do we go from discriminative models, which, like I said, typically do prediction, like inference on, for instance, classification of images, to generative models? So remember, in a generative model, you learn an approximation of a distribution, of the distribution of a data set, and you generate samples according to that distribution. So, this is an example of a GAN, a generative adversarial network, that, given enough pictures of cats, learns the distribution, learns how cats look like, and is able to generate a picture of a fake cat. Okay. So how do we do membership inference against generative models? So here now, again, let's assume we have a generative model in the cloud. So now your query is, please generate a picture of a car for me, or something like that, right? So now you no longer have the prediction, so the prediction, the confidence scores, right? So it's much harder to detect overfitting, right? So, and we worked on a paper a few years ago, and then since then the paper has been sort of improved and extended. But the main idea I wanted to share is to actually use generative models against generative models, right? So I apologize if you're not super familiar with things like GANs, but the main idea is that one typical generative model is called a GAN, a generative adversarial network, which has both a discriminator and a generator. So the idea of a GAN is to generate samples from the distribution so that the discriminator can really no longer distinguish whether a picture, in this case, is fake or real, right? So that's a main idea of GAN. Like also, GANs have been, extended. There is a million variants of GANs now, but this is the main idea. So we can play this game in reverse, right? So and we start with what we call white box attack, where we assume that the adversary, this is a very powerful adversary that is somehow able to steal the discriminator from the cloud model. So maybe through a leak or through like reverse engineering. Very often these models are deployed on like mobile devices or things like that. So the model, the adversary can maybe just reverse engineer the model locally. So, but let's start with this powerful adversary. So now, if I have the discriminator, I can actually sort of do take the samples that have the highest score from the discriminator. So we kind of go back to the membership inference attack against a discriminator. I can predict, that the top n scores, the records that have the top n scores were used to train the model, and that gives me a successful membership inference attack. Okay. So I should say that, in some cases it's quite bad from a privacy perspective to be able, for an adversary to be able to predict, to infer which records were used for training, right? So this is something that we want to protect. It's potentially, confidential information, it's sensitive information. Imagine you have a model that deals with healthcare data and, with prediction of, generation of healthcare data. You clearly want to avoid knowing that that model that maybe deals with cancer was trained on my patient records, right? Okay, so that's sort of the simplest attack, the white box attack. But a less powerful adversary would not have access to the discriminator, so we'll have to try and reconstruct it. So just by locally sampling things, sampling the discriminator locally, we'll try to reconstruct it and see if it's able to reconstruct those reconstruct those scores, and again make a prediction that the top scores, the records with the top scores, were used to train the model. So we did a bunch of experiments with mostly images. So we have, the sort of classic, the standard data sets that everybody uses, LFW, CIFAR10, and we also use an healthcare data set for diabetic retinopathy. So these are images of retinas, and there are models that learn to distinguish between healthy and diseased retinas. Okay, so we experiment with different target models, so like variants of GAN, DC-GAN, B-GAN, DC-GAN plus variational autoencoder. And we have, except for B-GAN, and here I'm not an expert in generative models, so I cannot, to be honest, I don't really know why we have a drop in accuracy. But overall, the accuracy of the attack in the white box model is pretty high. Like with DC-GAN, we get almost perfect accuracy in both LFW and CIFAR10. And this is compared to here the random guess has accuracy 0.1. And the reason is because we're trying to identify 10 out of 100 training samples. And so you can see that things are pretty okay, but not so much with black box. So in the black box setting, we have sort of maybe decent enough results for LFW, which are sort of maybe it's a little bit relatively easier data set than CIFAR10, but with CIFAR10 we're not doing very well. The attacker has an accuracy that is barely above the random guess, right? And things are somewhat similar with the diabetic retinopathy. The white box attack is very good. The black box attack is really, really bad. It's almost indistinguishable from the random guess. But if we assume that the adversary has some kind of auxiliary knowledge, let's say knows a few records that were indeed used to train the model, so as we assume that those records were public and others were private, and we're trying to reconstruct to infer membership of the private ones. So if the adversary can sort of learn a little bit more about the distribution of the data set by having this auxiliary knowledge, then the accuracy almost matches the one of the white box attack. So that points to all sort of possible improvements that we could do, and there have been papers after ours that have actually done that. So overall, this is the overview of the results. You can see white box attacks pretty accurate, black box attacks not so much. Auxiliary knowledge improves things significantly. And this is actually an idea of the visual quality, a visualization of the visual quality of the attack. So I'm not sure you can see very well, but the idea is that the more accurate the attacks are, the visual quality of the generated samples becomes better. Okay. At that time, there wasn't really much that we could do with respect to defending against these attacks. So there was a couple of attempts to build differentially private GANs, but unfortunately, there was a really clear trade-off between accuracy, like utility and privacy. So the attack would be not so accurate. So you can see on the left-hand side of the plot. I'll actually go back to explaining what epsilon is and what differential privacy is. But just to give you an idea, if you actually have strong privacy, which corresponds to low epsilon, you have low accuracy of the attack, but unfortunately the utility is very low. You can see the images are pretty much useless. So those GANs will not really generate any useful images. So maybe this is a good time to stop for a second, ask if there is any questions from the audience.
Or Emiliano, we take questions after 30 minutes after you finish, so that the recording is right. Yeah. Okay, sure. No worries. So how can we defend? So really, the idea is to do to use differential privacy. And there are different ways that we can do it, but the standard in sort of deep neural networks
is to add differential privacy, add privacy protection to the stochastic gradient descent algorithm. So differential privacy is a very simple definition that tells us that, I mean, this doesn't look very simple, but it is, trust me. So it just tells us that if I have an algorithm, this algorithm can be differentially private with two parameters, epsilon and delta. If an adversary for all outputs of that algorithm cannot distinguish whether that algorithm was run on dataset D or dataset D prime, where those datasets are exactly the same except for one record. Right? And really, this is an indistinguishability definition that tells us like everything is the same. I just change one bit. I just change one record, and now I run this algorithm on either one of the versions of the datasets, and I cannot really distinguish unless with some probability bounded by this epsilon value. Okay, and sort of the weaker notion of differential privacy introduces this delta parameter that allows for a small probability of failure. And we use this definition nowadays. It's just a little bit easier to work with. You just minimize that. You make that probability negligible, and that's good enough. So you can also use some useful properties for differential privacy, like post-processing, composition theorem. I'm just gonna go very quickly. So the one thing I wanted to focus on is the composition theorem, that if I combine k algorithms, each being epsilon differential private, then the resulting combination of algorithms is k times epsilon differentially private. So it's very easy to keep track of the privacy budget. And so a few years ago, we actually were supported by a Nokia grant, and we built a simple proposal for a differentially private generative model that allows us to have relatively good trade-off between privacy and utility, privacy and accuracy. So the idea is to split the data set into clusters using a novel private kernel k-means algorithm, and then apply noise and do the privacy preserving differentially private stochastic gradient descent on clusters. So because those clusters have data that is similar to each other, their sensitivity is lower, and the amount of noise that we need to add is lower, and so we can have better utility. So that's very brief, very high level overview of the idea. And so let me just skip this, just give you some ideas of the results. We tested on two generative models, restricted Boltzmann machines and variational autoencoders. And for utility, we actually look at the visual evaluation of the quality of the generated samples on the MNIST dataset. But we also have mobility data that we obtain from a telco, and we do counting queries, and we actually measure the accuracy of the counting queries. So here's just to give you a brief a high-level overview of the experiments. So when we used more noise, we get better privacy guarantees, which just tells us that things work as intended. And then we also see that we can play with the accuracy, we'll play with the clustering so that we have a good trade-off between clustering and privacy, and so that our algorithm for private kernel k-means actually works better than the naive way of applying differential privacy in k-means, and we have shorter RFF features that leads to better accuracy. Okay, so here is what I wanted to show. So you can see the original samples on the left-hand side, and you see what happens when we add privacy in the generation. So with RBM, you can see more or less you can still make out the numbers. Variational autoencoder, if you don't do the clustering, it's all useless. When you do the clustering, things are much better. So the visual quality is high. The drawback of this is that you can see very little variation very little diversity of the generated samples. And that this is a sort of a feature of differential privacy, in that it sort of kills the outliers so that you can preserve that distinguishability definition. Okay, I'll come back to this. I'll just sort of skip the content query for the interest of time, just to say that we improve over the state of the art. So the last thing I wanted to talk about is sort of drives on fairness, although I'm sort of misusing this term because fairness means different things to different people in AI. But the idea is to look at how differential privacy impacts different parts of the data sets when generating synthetic data, right? So, and we actually started from like our motivation was, from some recent results that shows that differential privacy has disparate effect on statistics, on deep learning classifiers, so more on sort of on deep discriminative models, which means that if you have unrepresented groups, so on the data sets, those groups are affected more by the noise introduced by differential privacy, and so they're sort of penalized more for privacy protection. So we thought we would do the same for generative models. So when you generate synthetic samples, are you helping or are you hurting class or subgroups that may be smaller? So think about, for instance, in a data set that has population, like you could have a group that has like with minorities, so that group is smaller, and you want to make sure that that group is not, you want to check whether or not that group is penalized even more by the introduction of the noise in differential privacy. So we did a bunch of experiments with sort of the state-of-the-art generative models, differentially private generative models, PRIV-based, which uses Laplace noise, DPWGAN, which uses differentially private stochastic gradient descent, and PATE-GAN, which is another approach that I don't have time to cover. So we have 4 data settings. We look at binary class size, multi-class size, single attribute subgroup size, multi-attribute subgroup size, and all different metrics for accuracy, precision, and recall. And we play with multiple privacy budgets so that we can measure subgroup imbalance levels. Okay, so these I admit these plots are probably very hard to read, but I'm just going to give you the also because I'm sort of running out of time. I'm going to give you the takeaways of our experiments. So first thing we ask is whether differentially private generative models generate data in similar classes and subgroups proportions to the real data. So do we preserve these proportions? And unfortunately, that really is not the case. So we distort this proportion quite significantly, giving us sort of these Robin Hood versus Matthew effects, depending on the generative models. So in a Robin Hood setting, you sort of steal from the rich to give to the poor, right? So and here I mean larger. The rich are sort of larger subgroups versus smaller subgroups, whereas the Matthew effect is, everybody is affected. So it really depends on the model that you use. The second question was whether training a classifier, sorry, that's the typo here, on the output of the generative model, so on the synthetic data generated by a differentially private generative model, leads to the same disparate impact on accuracy as training on a differentially private classifier on the real data. Okay, so the introduction of essentially the use of synthetic data, how does that affect accuracy on different classes or subgroups? And overall, this is kind of it's a good news in that smaller classes and subgroups suffer in a similar manner, so we don't see that much of a negative effect. However, everybody has reduced accuracy, which is what you expect from the use of differential privacy. And actually, we see that different models behave very differently. So it's very important that, you know, when you think about fairness, when you think about disparate impact of differential privacy in synthetic data, you are conscious of what model you're using, because some may affect, may compound the problem more. All right, so I'm going to stop here. I really would like to thank you for your attention and be open to answer any questions you might have. Thank you so much.